I asked Sora to make a video of a light pulse propagating through a sequence of lenses, and this is what I got. I'm not quite sure where the bloom is coming from. What I really want to talk about is the information in the field and how it may be destroyed in an imaging system, and especially what happens when we have a lens waveguide. Here's another view of this kind of thing. This one is from Dolly. We have a sequence of lenses, and two sequences in parallel, I guess, where light is coming through, and the light would come through, come to a focus, and then go and hit the next aperture and come to a focus again. This is a lens waveguide, and I want to compare the information that propagates through a lens waveguide for a coherent imaging system and an incoherent imaging system, and talk about what that means for the information in the system itself. So let's get to it. Computational imaging. Episode 52, Coherent Modes Revisited. Today's episode goes back and forth between a lot of episodes from this course. We'll reach, in fact, all the way back to episode 4 eventually in this video. But today we're looking at a slide from episode 36 where we talked about the impulse response and the transfer function for a coherent imaging system. And you'll recall that a coherent imaging system has this flat transfer function. So all frequencies between minus 0.5 over lambda f number to 0.5 over lambda f number are transmitted. And this is what the transverse cross-section of the transfer function looks like. It's basically the exit pupil of the system, but evaluated such that the band limit is at 1 over 2 lambda f number. And then, of course, this is the Airy pattern corresponding to the impulse response. Okay, so imagine that we go through a sequence of imaging systems in a lens waveguide. So we have a object here, and we're going to be let's say 2f away from our lens. So we're going to get an image somewhere here, which would be our object inverted, and then we'd go through another lens and we'd invert it again. So this is a sequence that would just repeat the lens every time. And so let's say this is 2f just for the sake of argument, and this is going to be 2f. And this is going to be 2f, and so we're just repeating this lens over and over again. Now, the image or the field is degraded from this first input to the first image plane. That transformation is a band-limited transformation, so we take whatever the field distribution is on the input, and we would convolve it with the impulse response. Where here we're considering it in one dimension, so we have this sink as our sampling function. So the image is blurred by the sink, but if we take the image and we image it again, it's going to be band limited again, but it's already band limited, and it has that constant band limit. So if we take this image of the field, convolve with the sink, and convolve it with the sink again, we get a second integral, but we can do the second integral first and have an impulse response from the object plane to the second image plane, but the convolution of the sink with itself is still a sink, and so that's the image again. So in this coherent lens waveguide, the image repeats after the first band limit. In principle, neglecting any edge effects and so on, the image could be continued indefinitely and just repeating over and over again without any further loss of information after the first system. Now here's a little test about how well we understand incoherent imaging systems, because as you'll recall, the impulse response for the incoherent imaging system is the sink squared. So if we have a object here at the first image plane, we're going to get the object but convolved with the sink squared. But what is that image at the first image plane? So this distribution here, if it's an incoherent object, this f is the emittance. That's the spatially incoherent field at the input plane. The irradiance or the power spectral density is delta correlated at the input. Now we've assumed in imaging systems that we will measure the irradiance here in the image plane. So the transformation is from the irradiance in the input plane to the irradiance in the image plane. And if we repeated that transformation, if we go to the next field, if we had that irradiance here and said we're going to image that irradiance here to the second focal plane, we'd convolve again with the sink squared. Now that leads to a degradation of the information. You recall that this sink squared is equivalent to the sink squared impulse response is equivalent to multiplying the Fourier spectrum of the input field by the incoherent transfer function, which is not flat. The incoherent transfer function has this triangular shape that we've seen over and over again. And then if I applied that triangular transfer function to the image in the second focal plane, it gets worse. It would get sharper and sharper, with the DC getting more and more accentuated. So is that what happens in an incoherent imaging waveguide, though? We need to think about this for a minute. So definitely, if we measured the irradiance here and then transmitted that irradiance, it would be blurred again. So as it goes down the waveguide, the image would get blurrier and blurrier. But we don't image the field here. We would take the field here, image it to this plane, but we don't detect it. We then relay it to the next plane, and that operation occurs on the mutual intensity or coherence function. The field here at the first image plane for the incoherent system is not incoherent. So this field, the input plane, is spatially incoherent. But after we filtered it by the lens, the field is not incoherent. That's what we saw in our episode 51. We derived the coherence transfer function, which is a relationship between the irradiance at the input plane to the mutual intensity here. And we saw that we could derive a transfer function to describe that relationship. Now, that relationship had this complicated form in the form of the ambiguity, the pupil function, and also had a triangular shape. It limits the bandpass of the system. So definitely, if we applied that transformation recursively, it also would lead to a degradation of the of the spatial frequencies with every relay. But that relationship is between f of x in the input plane and j of x bar delta x in the image plane. That's a relationship between the incoherent irradiance and the partially coherent mutual intensity. What we're interested in going from this plane to this plane is a transformation of the mutual intensity itself. And the mutual intensity is not transformed by the coherence transfer function. It's the impulse response for the mutual intensity from the input plane to the first image plane uses these coherent impulse responses, and then if we relay the mutual intensity from this plane from this plane to this plane, that would again operate on each of the variables, each of the x1, x2 variables using that coherent transfer function. So in fact, the mutual intensity after this first image, after we get to this first plane, the mutual intensity in each subsequent plane uses the product of the coherent transfer functions and is invariant. So in fact, with an incoherent waveguide, after the first image plane, the field from the first image would be relayed without any loss of information to subsequent image planes. Now, the reason that this is so interesting is that clearly if we had the irradiance here and relayed the irradiance, we would be losing information in each step. And what this really points out to us is that there's information in this mutual intensity in each of these planes that's lost when we project onto the irradiance. That information we're going to talk about today, and if we could detect that information, we could make digital imaging systems that capture more information. The assumption that digital imaging systems only capture irradiance is just that, an assumption. Perhaps we can design them to measure the mutual intensity. To understand what it would mean to sample the mutual intensity, we step back to this slide from episode 4 of our series introducing the Whittaker-Shannon sampling theorem. And of course, you'll recall that the sampling theorem says that if we sample the signal with a period equal to or smaller than the Nyquist period, which would be 1 over twice the bandwidth, then we can exactly represent a band-limited function. So here we have this function f of x sub b, which is f projected onto the band limit of u is between minus b and b. If we sample that with these discrete samples, f of n over 2b, then we can use this interpolating function, the sinc, to exactly reconstruct the signal at any value of x. Now, when we sample a image in the focal plane of a camera, we're sampling the irradiance. The irradiance is band limited, so if we sample at better than Nyquist, even though the band limit is not square, we have this MTF and fall off in frequency response, the radiance is still band limited, and so if we sample a sub-Nyquist, which would be 1 over better than 1 over 2 lambda f, then we could exactly reconstruct the irradiance. But we cannot exactly reconstruct the mutual intensity, which also describes the field, because as we've just seen, the irradiance is not a complete descriptor of the mutual intensity. Of course, the mutual intensity is jointly band limited in each of its output variables. So in the focal plane, for example, we're going to measure the mutual intensity at points x1 and x2. And the mutual intensity consists of the convolution in x1 and x2 with the coherent impulse response in x1, the coherent impulse response in x2, with the remote irradiance image. So it's jointly band limited in x1 and x2. The sampling theorem applies in each of those coordinates, and so we can exactly represent the mutual intensity with samples drawn at discrete points, x equals n, and where x now is in units of lambda f number, and x equals m. And so these discrete samples, or this J matrix, would represent the mutual intensity, and we can reconstruct the mutual intensity exactly by interpolation on these samples. Let's look at an example. Here we've got a source consisting of 2 point sources, a point at x equals a and a point at x equals b. So here's our source, points x equals a, x equals b, and they each have an intensity I sub a and I sub b. According to our formula for the samples of the mutual intensity, we convolve with these sinc functions, so we could replace each of the point sources with a sinc. And what you notice is that the mutual intensity for these two sources is the mutual intensity for each of them individually added together. So because the sources are mutually incoherent with each other, their mutual intensities add. So we have a matrix for values n and m of the sinc evaluated at the sinc at position A, the position of the first point source, of x minus n evaluated at the sampling position n and m. Okay, so this matrix forms our J and M. We can look at the structure of this matrix and evaluate something about the underlying mutual intensity. And so that's done on GitHub, on the course GitHub site. There's this notebook on coherent modes to look at the structure of the mutual intensity matrix for various samples. Here's examples. So let's suppose we have 1 point source. Now in this case, the point source happens to be located at 0, so x equals 0. And so we only get one mode, that basically J and M only equals 1 for n equals 0. And so here we've evaluated the mutual intensity at discrete sample values, n and m going from minus 16 to 16. So we have 32 samples in a one-dimensional sampling system. And if we have one point source, then we can look at the eigenvectors of the J matrix. Those eigenvectors correspond to eigenvalues. In this case, in the upper left here, we have 1 point source. We get one eigenvalue equal to 2. There are 16 eigenvalues in the matrix, but the eigenvalues 2 through 16 are equal to 0 in this case, because there's a single coherent mode. Now, here's where we have 2 point sources. So down here at the bottom, you see the field that's exciting the source here. And in this case, we have a source at minus 0.1 and a source at plus 0.1. And now we get the first mode has an eigenvalue of basically 2, but a little less than 2. And the second one is 0.06, so small, but not 0. And so the J matrix is a representation on the sinc function of the mutual intensity. But we can take then, the sinc is an orthogonal basis for representation of the mutual intensity. And we can find combinations of the sincs to generate new modes over J. And what we see here is that if we take weights of the sinc samples with the weights shown by this eigenvector, we get an eigenfunction of J, which corresponds to a coherent mode. And so here we have 2 significant coherent modes. Here we've taken the 2 points and we've made it asymmetric, so one of them is at 0.1 and the other one is at 0.4, and we again get two modes, and here's only two eigenvectors are plotted because the third eigenvector has a very small eigenvalue. But the value of the second eigenvalue is still about the same as it was when the 2 point sources were centered on the origin. Here we've moved them much further apart, so you'll see less interference between the 2 points. Or the points, of course, don't interfere, but we have less ability to get one of the modes to null because the 2 points are far enough apart that they start to be separately observable. And so here we have two eigenvalues that are both equal to 1, and basically those two eigenvalues correspond to imaging the point sources individually. Here we have 3 point sources, all located relatively close together, one at the origin and one at minus 0.3 lambda f number and one at plus 0.3 lambda f number, and we get 3 modes. So you can think of it like a different mode for each one of the point sources, and if we evaluate the amplitude of these 3 modes, we can say something about the separation of those point sources. Here as a final example, the 2 points, all the previous examples, the 2 points have equal intensities. Here one of them is 10 times as intense as the other, and you see we still get we get a large first eigenvalue because of the increase in the intensity of one of the sources, but we still have a non-zero second eigenvalue, which we could use to try to resolve the separation between the 2 point sources. Reaching back to a previous episode again, recall that in episode 46, we derived the coherent modes for a 2 point source system where one of the modes was the derivative of the fundamental impulse response, and we showed that the eigenvalue for that second mode is proportional to the separation between the 2 eigenvalues. So what we're doing here is finding a mode that would try to null the signal from the 2 sources. When we have exactly one source, we have one mode, and we can get a null in all other measurements. With 2 sources, we can no longer get that null, and so the smallest second eigenvalue we can get is proportional to the separation delta between the 2 point sources. Now, in the simulation that we are looking at here, we have 2 point sources on this J&M matrix where we've done the Nyquist sampling of the mutual intensity. We can look at the amplitude of the second eigenvalue as a function of the separation between the 2 point sources numerically. So we just go into our matrix generating J and change that separation and plot the amplitude of the second eigenvalue as a function of delta. And what you find is that it goes as delta squared. So this is a log plot where you see this line, and the amplitude of the second eigenvalue is going like delta squared. So the slope of that line is 2. And so we could analyze the second eigenvalue if we project J onto this sinc matrix, and then evaluate the separation between the 2 point sources. And of course, we can analyze similar behavior for a variety of distributions now that we have this structure for representing and sampling J with Nyquist sampling. So, everything's well and good if we can measure J, but of course we cannot directly measure. We can use those Shannon samples to describe J and M, but the off-diagonal coefficients of J are not directly observable. Any measurement we're going to make is a projection onto a mode, the irradiance in a particular mode. So for example, we choose this mode phi and measure the irradiance in that mode by integrating the mutual intensity over the mode in each of the output variables. Now, of course, we could represent phi as a vector projected onto the band-limited basis. The mode phi, the measurement mode, is not necessarily band-limited, but only the band-limited parts, only the parts within the band of J would have a non-zero integral with respect to J, so we can project phi onto this sinc basis, sinc in this case being our one-dimensional impulse response, but of course in 2 dimensions we could use a basis function that fully described J in the 2 dimensions. But we represent phi by this matrix, or by this vector, and then the measurement consists of the vector matrix product with the J operating on phi and phi dagger operating on that matrix to give us the intensity in the mode phi. Now, the measurement over a single mode is not going to characterize J, so we need to make a measurement over several modes in order to characterize the underlying mutual intensity. And so we build this matrix big phi here, where big phi is equal to a matrix with each column equal to phi 1, phi 2, and so on, the distributions for each one of the modes we want to measure, and then we operate on this phi with J, and then to project onto those modes, and then operate with phi dagger to get the intensity in each one of those modes. We're only interested in phi 1, the product of J times phi 1 and phi 1 times that, which would give us the intensity in the phi 1 mode, and so we are interested in the diagonal of the matrix products of J operating on phi, and then phi dagger operating on that product. Take the diagonal, and we've got the intensity in each one of those modes. Now, this big matrix phi typically is not going to be a square matrix because, as we've seen, measurement of J just on a set of modes equal to the underlying number of coherent modes, or the underlying number of coherent impulse responses, is not sufficient to describe J. For example, if phi was a diagonal matrix, then we would be measuring the conventional irradiance in the focal plane, which is not sufficient to fully characterize J. So typically we'll add additional modes. For example, we could make phi the set of modes of the impulse response and the set of derivatives of the modes of the impulse response. We could make phi a set of Hermite Gaussian modes that is over complete in the band limited distribution in order to fully characterize J. Now, one ideal measurement, of course, would be to make phi this matrix phi the set of the eigenvectors of J. J can be represented as in eigenvector form as U, lambda times U, make this U dagger. And this would be the diagonal matrix of the eigenvalues. So if we measured with the eigenvectors, then we could characterize the eigenvalues in the field, and we'd have a full characterization of J. The problem, of course, is that we don't know what the eigenvectors are, because as we've just seen, the eigenvectors of J depend on the source distribution. So our goal, the reason we get more information by measuring the mutual intensity, is we get the values of the eigenvalues, which is 1 for each mode, and we get the structure of the eigenvectors, which is characteristic of the source as well. Any measurement that we make can be described as a projection onto the onto the coherent modes, the eigenvectors of J. So those are represented here from something we had way back in episode 46, where we described the coherent modes. And so this is a non-negative weighted sum of measurements of these eigenvalues. Obviously, the entropy in G would be ideal if each one was an individual measurement of the eigenvalues rather than mixing the eigenvalues together. So we need to figure out a strategy for characterizing J from these kinds of projections. This process of characterizing a matrix from intensity projections basically has a name. It's quantum tomography. This is a common problem in figuring out the density matrix of a quantum system. So very similarly, the density matrix is, by definition, a matrix, and we can only measure the state of individual modes. And so, this process is common in quantum computing and other quantum systems, where you have to figure out a process for measuring the states of modes in order to characterize a quantum system. Now, in this case, the density matrix consists of the mutual intensity, and so we need to figure out how to characterize the mutual intensity from projections. It's a big, complicated topic in general, but in these incoherent imaging systems, it's not as complicated as it might seem, because the J matrix is not fully populated. It's typically going to only have values close to the diagonal, because the field in the focal plane, while partially coherent, has a very limited coherence length. So we're imaging a remote incoherent source. The band limit causes the image plane field to have some partial coherence, but the coherence cross-section, the range over which the field might be coherent, is going to be just a few multiples of lambda f number. And we know that because of what we saw in episode 51 when we looked at the coherence transfer function. We have this variation of the coherence transfer function as a function of delta x, but it falls relatively quickly as a function of delta x. So if you go out to delta x is 2 to 5 or 10, the transfer function is going to go to 0, and so we only expect j to be non-zero for delta x equal to something less than, let's say, 5 lambda f number. But of course it falls as the sink, so it could have relatively long tails. This is a simulation using the same approach as we used with the point source distributions in the previous slide, where we can calculate what j is for the band-limited system by finding this matrix J and M. Now, in this case, we're looking at a source that is confined to the range from minus 16 to 16 lambda f number. So we have, in this case, 64 samples, but we're only showing the central 32 samples in the J and M matrix. What we see on the right here is the matrix itself. So this is the J matrix. And this is for, first of all, 16 sources that we've randomly distributed. So on the range between minus 16 and 16 lambda f number, we've randomly chosen with uniform distribution the position of 16 sources and then calculated the resulting J matrix. In this case, we have 16 eigenvectors. So there's 16 eigenvectors with a non-zero eigenvalue, and these are the eigenvalues, or the eigenvectors. This is the right singular vectors of the J matrix. And what you see, so only these first 16 or so correspond to non-zero eigenvalues, and you see that the eigenvectors are kind of distributed, that they have a lot of non-zero values over the range between minus 16 and 16, which is 32 elements here. Now, if we increase the number of points in the object, so here we've gone to 32 points, now we don't quite get up to 32 eigenvectors. So even though we have 32 points, the eigenvectors that they generate is not complete on all of the points, but it's more than we had with 16, and now we have a different distribution in our eigenvalues. Some of them are very localized, meaning probably that this is the J matrix, and you might think that, like, we had a lot of intensity here, we don't have much intensity here, so there's no eigenvalue describing this region or this region, and then we've got the points kind of clustered in here. So we get a structure, but one thing you see, with a relatively sparse set of eigenvalues, we have a lot of coefficients of J off the diagonal. As we start to add more points into the system, the intensity of these mutually incoherent points adds. So down here we've upped it up to, we have 1,024 points in this, or 1,024 point sources in the range between minus 16 and 16 lambda f number. Their intensities all add, so the J matrix starts to look kind of diagonal, because the off-diagonal terms are bipolar and the on-diagonal terms are non-negative, so they tend to start to dominate. And in this system, it would be difficult to get information off the diagonal, but you could measure the intensity of the system. You see that the eigenvectors tend to become very localized. Now, as we increase the number of points, the band-limited number of non-zero eigenvectors we could expect to get here, the number of coherent modes is going to be 32. So we increase the number of points, the eigenvalues get kind of flat, and the number of eigenvalues, or the number of non-zero eigenvalues, tops out at 32. So in these different situations, first of all, we're going to find that if J has some sparse structure, doesn't have to be sparse in the obvious basis, but has to be sparse in some way that would allow the side lobes to become interesting. Doesn't allow them to be suppressed by the total domination of the irradiance along the diagonal. Then we have structure that we might want to reconstruct, but the there's no measurement in the J value, way out here at the edges of the matrix. It's all going to be kind of clustered around the diagonal. So we have the challenge of figuring out how to extract that information. We've seen that we could use an interferometer for 2-point sources over the full array of the aperture. We've seen in this lecture and in lecture 46 that we could project onto some set of ideal modes, and we have the problem of how to find those modes. This chapter, chapter 8, has mostly been around how to describe the coherence of the field. In order to really understand how to measure the field or how measurements work, we need to understand discrete sampling systems in more detail. Discrete sampling is the subject of Chapter 9, which we're going to get to in a couple of lectures. And so we'll develop a much more sophisticated way to understand how we turn continuous distributions into discrete measurements and how we process those discrete measurements. And then in Chapter 10, we'll start to talk about ideal design of focal planes, what we should be measuring when we want to measure time, polarization, and spectra. It's going to take us a while to get up to where we're comfortable talking about how a focal plane might incorporate coherence measurement, so we're going to save that until the end of Chapter 10. Next time, we're going to talk a little bit, though, about how we could characterize the mutual intensity matrix, basically, by having some sampling diversity in the point spread function of a system. Now, here's an example of a planoptic camera. This is an analysis of a planoptic camera that was published by my colleague at the University of Arizona, Jim Swigerling, in 2013, where he was looking at the aberration in a planoptic camera. A planoptic camera uses a lenslet array to create multiple samples of the focal field as it coming into a camera sensor, but you can understand this as a strategy for getting multiple samples of the mutual intensity locally in the field. Now, I'm not a fan of planoptic cameras for reasons that we'll get into in Chapter 10 when we talk about sampling structure. This is kind of a rigid sampling structure that gives away resolution. It's much more interesting for us to think about adaptive sampling and for sampling diversity that is more matched to the field. But one thing I like about this particular design is it emphasizes the fact that we don't have to do the same sampling at every point in the field. So we'll look a lot at camera arrays and strategies to get diversity of sampling. And one kind of camera array, for example, would be have an array with different MTF, have an array with different focal lengths, have an array with different aberrations and different strategies for sampling the field. And so next time we'll talk about would there be some advantage to sampling the field with a different PSF.